have two populations and we want to compare variances, just like what we did the other time when we're comparing means. We're comparing proportions, but right now we are actually comparing variances. Or you want to compare the standard deviation. Before I start this topic, I want to tell you this. In algebra, because let me tell you this, I want to say what is very, very important in every aspect of mathematics. We do algebra. Now, if I'm going to talk about difference between two things, the algebra I can use is either to subtract or to divide. I'm going to say that again. If you want to look at, if we're comparing two groups, it's either you subtract or you find a ratio. Now, I could remember when we're dealing with the population mean, difference of the population means, when we were subtracting, and when we constructed an interval, when the interval includes 0, we say there is no significant difference, right? We did that for population means. We also did that for population proportion. But let me tell you this: when we want to talk about comparing population variances, we don't subtract, but we divide. We do ratio. If the ratio gives us 1, what does that mean? They have the same variances. Now, what we're going to be looking for in the interval, when we're comparing two population variances, the population variances are the same if the interval include 1, not 0 anymore. Because we're going to be talking about ratio. We are not going to be talking about subtraction. I want you to take note of that. Okay, like I said, we actually want to compare, we actually want to construct a confidence interval for the ratio of the two population variances. We are not going to be subtracting. We're actually going to be a ratio. And if that is what we have, we're also going to have assumptions. In statistics, all statistical methodology have assumptions. A model is as good as assumption putting into a model. Okay, assumption number 1, since two populations are involved, we got to make sure that we take a random sample from two populations, and the two samples have to be independent. And not only that, both have to be normally distributed, the two populations. Then from there, oh my God, if I want to get a point estimate of the difference of variances, I'm just going to do ratio. You know, when I was in elementary school, when I was in high school, we normally ask a question: why are we dividing? Why are we subtracting? Why are we multiplying? You can now see the reason why we're doing that. Oh my God, mathematics is very, very useful in the world. Now we're finding the ratio. We're going to find the ratio of two sample variances now. Okay. And of course, it's either the ratio give 1, or something greater than 1, or something less than 1. Okay. Now since we're going to be comparing two variances, the distribution we're going to use will change. It's going to be F distribution. You remember the other time when I was talking about one population for the variance of standard deviation, we use a chi-square distribution. We were checking from a chi-square table. But right now, since we are actually interested in the ratio of two variances, the distribution is going to change to F distribution. Okay? And that is the shape of the F distribution. And you know what? We're going to have 2 different degrees of freedom, because we're taking sample size from 2 different groups. The degree of, because when you look at the F distribution is going to have the degree of freedom for numerator and the degree of freedom for denominator. Okay, so, and the degree of freedom for the first one is going to be, okay, how many sample size do I choose from the first group? I'm actually going to subtract 1 from that and from the other group. Okay, And let me tell you, I will quickly show you something now on the, look at that. This is F table. For those of you that are going to use table in the exam, we have a lot of tables. Now this is an F table now. This is how the F table look like. You can see the numerator degree of freedom, denominator degree of freedom. The numerator degree of freedom will be for one, the degree of freedom for, for the sample taken from one population and the degree of freedom taken from the other population and under a certain level of significance. Let me take you to an example now. Take a look at this. Consider the following information from two independent samples. In the first population, they choose sample size of 18. In the second population, they choose a sample size of 25. And the sample variance from the two are available, and they ask you to construct a 95% level of confidence. If you want to do that, the very first thing you actually, let me first show you this. Before you do that, I'm going to show you the formula. Give me 1 second. Now take a look at this guy here. If I want to talk about the interval estimate of the ratio of population variances, this is the formula. Like I told you the other time, you don't need the margin of error. You're just going to go straight to the formula. If you take a look at this formula now, the difference between the lower end point and the upper end point is F. Look at that, F alpha over 2 here, and there F1 minus alpha over 2. It means when we go to the table, we're going to check for two different values for F. That is basically what we're going to do. If I want to talk about the ratio of the standard deviation, you know what is going to happen? I'm going to show you that one. You're going to find the square root of all of that. Oh my God, take a look at this now. This is when I'm talking about the ratio of standard deviation. It's just the square root. Take a look at that. Okay, now if this is what you have now, so let me now take you to an example here. Now in the example, you are given this, and they ask you to construct the interval estimate for the ratio of the estimate of the population variance. The very first thing you do, you get a point estimate. The ratio, look at that. That gives you 1.033613. Take a look at that. This is a point estimate. Okay. Looking at the value like this, we know that the ratio is not equal to 1, but we don't know whether it is statistically significant. We don't know that. And for only way to investigate, okay, whether it is statistically different from 1 is to construct an interval. Now, because of that, I needed to go to the table of F. The level of confidence given was 95. If you look at the question, was 95. Then I need to get the alpha. Alpha will be 1 minus level of confidence, right? The alpha will be 0.05. After getting the alpha in 1F, I'm going to do alpha over 2. In another F, I'm going to do 1 minus alpha over 2. But before I do that, I can find the degree of freedom for the first one and the second one. But I need to separate degree of freedom. Okay, now look at the degree of freedom that I have now. It is now time for me to go to the F table. What do I want to go? What do I want to go and check for in the F table? The one for alpha over 2. Okay, I will check under the 2 degree of freedom for 0.025. And we also check under 2 different degree of freedom. Okay, for the other one for 1 minus alpha over 2 for 0.975. Now let's go now. Take a look at that. 17 against 24. 17 degree of freedom against 24 degree of freedom. I'm actually going to check that. Look at the area. It's 0.025. Then I will go to another table because the F table we have different F table where you have the area. The area here is 0.025. There's another one is 0.97. So I'm going to check for that one too, and we're going to get the result. Okay, so what I'm trying to tell you now, okay, for a 0.975, which is this one to check from, look at the area. Okay, when I check for 17 and 24 under that gives me 0.3907. And all what I just need to do, go to the formula, you just plug them in. Okay, when you plug them in, then you have your result. And let me tell you this. If you really want to understand, lastly today, I will quickly walk you through an example that you're actually going to see reason. Suppose that a quality control inspector want to make sure that two different machines are filing soda can with the same level of precision. Because there's possibility that two different machines, they may not have the same level of precision. And maybe that may contribute to the variation in products. Maybe it may be due to machine. Okay, now specifically, she wants to ensure that the population variances of the amount of soda per can are the same for the two machines, and random samples of can filled by the two machines are taken. The amount of soda in each can is measured in millimeter, and the variance of the amount of soda is calculated for each sample. And you know what? It chooses a sample of 16 can from machine A. Okay, and that one has a variance of 0.93. And while a sample of 18 can from machine B that has a sample variance of 0.36, assuming that both populations are normally distributed, construct a 90% confidence interval for the ratio. Okay, what are you going to do? From machine A, this is a data set. For machine B, you have your data set. The next thing you're going to do, get a point estimate of the difference of the ratio. Look at that, the point estimate, the ratio of the two, that gives us 2.5. That's a point estimate. Now, the next thing you're actually going to do is getting the critical values of F. And to get a critical value of F, you need to get your level of significance from the level of confidence, getting your alpha, then you get alpha over 2, then 1 minus alpha over 2. And of course, you need to go to the table to check. And when you go to the table to check, I want to tell you that what I check in the table, now since we're using that formula, when I check in the table, okay, for the other one is this guy, and what I check is for the table is the other one. Always, what I want to tell you in the lower part, the F in the lower part will be bigger than the F in the upper parts. Okay, every other thing will remain the same. And take a look at this. The ratio is this. Now, I want to award an extra credit now. Okay, now I wanted to say this. Is there significant difference, okay, between the two machines in what they turn out? Can somebody tell me? Okay, go ahead. Oh my God, look at me, because it does not contain 1. Send a message to me for extra credit. You know, here we don't talk about 0 anymore. We only talk about 0 when you are subtracting, and that only applies to population means and the population proportion for the variances. You check whether there's a 1 in the interval. Because there is no 1 in the interval, then what that means is that they are not the same. This is the same thing as somebody who's looking at the effect of machine on what is being produced. A researcher can use a linear regression for that. Another researcher could use this. They are doing the same thing. Okay, so here we're trying to say the two machines, they are not the same in terms of what they produce. When we're looking at the consistency, we look at the variance. Look at that. And that was why I said we are comparing the two population variances to see if they are equal. If they are equal, their ratio will be equal 1. And since both endpoints of the confidence interval are greater than 1, then the sample data provide evidence that 90% level of confidence and the population variance of the amount of soda per can is greater for can filled by machine A, okay, than for can filled by machine B. We need investigation. We need to do research. If we want to understand the world we live in, we live in a probability space, and the only way to understand is to conduct research. And that is exactly what we have done. Okay, this is another example. But this time around, this is an example on population standard deviation. Now take a look at this. A family nurse practitioner is comparing the variability of a normal body temperatures for infants and adults. Infants and adults. You are comparing normal temperature. Specifically, she wants to know if the population standard deviation for normal double body temperature is the same for infants and for adults. A simple random sample of 28 of an infant patient normal body temperature measured in degree Fahrenheit revealed they have a sample standard deviation of this. And he did the same. He collected 25 for the adults and have a standard deviation of that. And you have to construct 95%. You're going to follow the same way. These are the data set from the two. For infant, for adults, you get a point estimate for them. Okay, and after getting the point estimate for them, do the same, go to the formula, okay, plug them in. Oh my God, at the end of the day, I got this. Oh, look at this one include one. What does that mean? The body temperature for adults, the normal body temperature for infants and adults are the same, because there's one in the interval. I think I'm going to stop here for now. Oh, this is even the last page. And it says, since a ratio of 1 will mean that the numerator and the denominator are equal, and the value of 1 is in this interval, data do not provide evidence at the 95% level of confidence that the population variances of the normal body temperature of adults and infants are unequal. So which means they are the same. If you enjoy today's topic, I need your hands up. If it is interesting, today's topic. Oh, okay. That's okay. It's interesting to me as well. Okay, so make sure you stay safe and have a very good day. Yeah, thank you too. Thank you. Have a good day. Make sure you stay safe, okay?